Okay, great. All right. First thing we're going to do is the first experiment there with Alka-Seltzer and water in the Ziploc bag. Okay? However, instead of a Ziploc bag, we're going to use a beaker. Okay? So, I've told you about Alka-Seltzer a couple of times, but this is what it looks like. Okay? It's a little tablet, nothing crazy. Okay? And all we're going to do is I'm going to fill this up with some water. I'm going to drop it in. Okay? You see how the bubbles are created? Hold it here so they can see too. Okay? All right, so what happens, all right, is the tablet reacts with the water and the carbon gas is being produced. What happens to the carbon gas? Jacob? How? What tells you the carbon gas is escaping? The bubbles. The bubbles are the carbon gas. So, in this reaction, we're actually forming a new substance, carbon dioxide gas, which is a chemical change. Okay? The tablet reacts with the water, and the bubbles keep evaporating. Now, bubbling out. It will continue reacting until the whole tablet is dissolved. Okay? And there's no more bubbles left. Yes? Alka-Seltzer. Yes. So, like, this is like if you want to take the Alka-Seltzer as medicine to help with like indigestion, gas, and heartburn and stuff, you would just drink this. Seltzer water, I don't think has Alka-Seltzer in it, but it has a similar something to it, I guess. I don't really know.
And it makes carbon dioxide?
Carbon dioxide gas. As it bubbles out. Okay? Brooklyn?
No.
It doesn't fill up. Water? More like soda, actually. Yeah. Like, not sweet soda, but like just carbonated water.
It is just carbonated.
That's pretty much all it is, yeah. All right, next one. Okay, the next one, we have our supplies. We've got a Ziploc bag. Okay, then we have these water jelly beads. Okay, these are kind of like Orbeez. Remember Orbeez? Okay, so these are little beads that you add water to, and the beads kind of absorb the water and kind of swell up. Okay, all the water is contained inside the little bead. Okay, so, kind of like vacuoles, yeah. These would actually be a good example for vacuoles, probably. All right, so I'm going to put in about 2 tablespoons of water beads.
3 tablespoons water.
I know it says 3, but I don't want. I'll do 3, I guess. I didn't want to use all of these beads, but y'all are the last class, so go big, right? All right. Next, we're going to add a teaspoon of what? Iron filings, okay? Really just little tiny shaved pieces of iron, okay? What happens when you combine iron and water? Or metal and water? It rusts. Very good, okay? What color is rust usually? Kind of brownish orangish, right? So, ideally, we should have the rust turn orange as it combines with the water and the beads. But the water is trapped in the beads right now. Okay? So we're going to add one more material. We're going to add calcium chloride, which is just little white pellets, basically. Okay? And the calcium chloride is going to react with the water beads to draw the water out of the beads. Okay? Now, when the water comes out of the beads, as the water reacts with the rust, Connor, how does this feel?
It feels really hot and squishy.
It's very hot. Okay? The iron rusting reaction is actually what's called an exothermic reaction. Okay? That exothermic reaction creates heat. Okay? This is similar to what happens with hot hands. The little packets that you put in your pocket to keep warm, you know? Okay? That happens in a similar way, just without little jelly beads in it. Okay? So I'm going to pass it around and let you feel it. Okay? You can feel the iron kind of heating up. You can also see the water coming out of the beads. Over time, the beads will get smaller and smaller as the water comes out. Okay? Now, don't squeeze it hard or it'll pop. Okay? So just kind of feel it with your hand. Brian?
Doesn't it take like a very long time for metal water to react to rust?
Yes. Okay? So we'll actually, can you see, Luke, hold it up. You see how the water's turning orangish, kind of reddish? Okay? So the rusting is beginning to start, but it won't actually turn completely orange for a while. Yeah. Okay? Yes?
So, if those iron filings, aren't they just like, or filings, aren't they just like filings from a nail?
From some kind of iron or metal, yeah.
Could you just drop like iron and water in a bag and then heat up?
Well, no, because okay, let me read the explanation. You know that leaving unprotected pure iron, usually nails I think are a little more like steel than iron. I don't really know. Of any kind, exposed to the elements outdoors will produce iron oxide or rust. All it takes is water in any form and the iron will be quickly covered in rust. A byproduct of the rusting process is heat. Hand warmers that you buy usually have a porous pouch containing a mix of iron powder, activated charcoal, salt, and vermiculite. The activated charcoal is very porous that holds the water needed for causing the oxidizing or rust reaction. Okay? I guess you could try it, but I don't know why it wouldn't work. Maybe if you had just like a pure iron metal or a pure iron nail. I don't really know. Okay? Let me hold it up so you can see that color over here. Okay? Maybe we should add some more.
Add more time to make it burn.
I want them to be able to feel. Alright. There you go. Okay? So, that's experiment 2. The iron reacting with the water, the byproduct of that rusting reaction is heat. Okay? And you can see obviously the change in color there of the water turning kind of more orange. Okay? Alright. Next one.
I think I'm gonna make this blue color.
Did you write your observation? It's in the next page, I think. Alright. Huh? Yeah. Okay, so this one, I've got my flask. Okay? Jacob, you with me? Got my flask. I'm going to fill up with vinegar, which I hate because vinegar smells awful. Okay? Alright, and then Jacob, you can come on up here. Okay? I've got a balloon. In the balloon, I've got baking powder, baking soda. Okay? I'm going to kind of wrap the balloon over the top. I'm going to hold it up, okay? When you're ready, just take the balloon, tip it up.
Whoa!
Whoa! Okay? No, it won't.
Whoa, it's filling your
Yeah, it's a whole. Okay, so the baking powder, as it reacts with the vinegar, okay, the baking powder is a base, all right? The vinegar is an acid, it's acidic, okay? The acidic vinegar and the non-acidic baking powder, they react to form 2 new chemicals, okay? One of those new chemicals, I can't remember the name of this number, but I'll tell you in a second. One of the new chemicals, as it begins to decompose and break down, releases carbon dioxide gas. As that gas tries to escape from the flask, I'm trapping it in the balloon. Okay? Which is what causes the balloon to expand and blow up. Okay? Now, there's a little hole in the bottom of it, so it's kind of leaking. You hear it?
I hear it. Yeah.
The gas produces carbon dioxide gas. The same kind of gas that we expel when we breathe out. dioxide. It's the same as if we were to blow the balloon with our mouth. So it would stay. See?
Oh,
It's heavier than oxygen. Okay? Micah. Yes, I'll take that back. Okay? Alright. Next, the yeast experiment. Alright. So, for yeast, we talked about before, yeast is in what kingdom? Brian? Fungi. Okay, it is a fungus. It's unicellular. Okay, it's also what you use when you bake bread. Okay, part of the chemical reaction that bakes the bread is the yeast in there. Okay, now instead of mixing the yeast with water, we're going to mix it with hydrogen peroxide. Okay, now this is the same kind of hydrogen peroxide that you can buy at a store, is what your mom might use when she cleans your cuts, things like that. Okay, this is 3% hydrogen peroxide. So I'm going to pour about a quarter cup or so into my beaker. Okay. Then we'll add a teaspoon of yeast. Okay. And then I'm going to stir it up. You can see it a little bit. You see it kind of starting to foam?
No, I don't.
Foam. This is a stick. All right. So I'm going to stir this up. Now, what is the formula for hydrogen peroxide? Anybody remember? I've told you like once, maybe twice. Well, water is H2O, right? Hydrogen peroxide is H2O2. Okay? The yeast with the H2O2 actually causes a reaction with the hydrogen peroxide, and that extra oxygen atom that's in the hydrogen peroxide, it releases the extra oxygen, which is what you see as the bubbles. Okay? Now, technically, this should be an exothermic reaction. Okay? It should cause the glass to heat up, but I don't think we have enough reacting for it to do that. But it would be exothermic. It would cause it to heat up as well. Okay? But you can even see now, you see how it's foaming a little more than it was? Brian? We're not going to use it because it's not really changing we would use a thermometer to measure the change in temperature, but it's not really changing enough for it to make a huge difference.
So is that kind of happens to salt water or
I don't know. That's a good question. I don't know if it's yeast or something else. Great question. Yes. No. See, look at it now. You see the foam growing?
Yeah. Oh.
Okay. So the yeast is still reacting, creating more and more bubbles. I'm going to let it sit, okay? And we'll come back to it in a little bit or see if it grows at all.
Oh my god, that looks kind of like it kind of looks like
Okay. Now, the next one, okay? The next one, I'm also going to use hydrogen peroxide, but this hydrogen peroxide is 30%, okay? So this one is 10 times stronger than what you would buy in the store. You can't buy this in the store. You have to order it online from this is from California Science Institution, okay? Typically, you only order it if you're in a lab or something like that. But because it's 30%, I'm going to wear gloves. Why? Aiden?
because, well, one, it's chemical reaction, you don't want to burn yourself.
Mm-hmm.
And two, it might overflow and you don't want to burn.
Essentially, yeah. That's why, okay? It's so much stronger than regular hydrogen peroxide, and I don't want my hand to burn, okay? So, I'm going to take my, oh, you came just in fast. This is cool. All right, so here's my graduated cylinder, okay? I'm going to fill my hydrogen peroxide up to 30 milliliters, all right? So, here's my hydrogen peroxide. Okay, 30 milliliters. Now I'm going to add a squirt of soap. Okay. Now notice, look how the soap sits on on top of the hydrogen peroxide, right? Why is it on top of it? Brooklyn? Is it more dense or less dense? Uh-huh. Very good. The soap is less dense, so it's sitting on top. Okay? Wyatt, pick a color. Green, red, or yellow? Red? Okay. We're going to add our squirt of food coloring here. Okay? Now, we want to mix it up. All right? So, again, hydrogen peroxide, soap, and food coloring. All right? Now, we're going to add our catalyst. Okay? A catalyst is what causes the reaction to happen. Okay? Earlier this morning, I came in and I saturated, or tried to saturate this water with potassium iodide. Okay? Do you remember the experiment we did on the computer where we had to keep adding stuff and trying to dissolve it until it just couldn't do it anymore? Okay? That's what we tried to do here. So I have a lot of potassium iodide in here. Okay? I'm going to pour it into the cylinder, and let's see if we can get a reaction out of it. Whoa! Whoa! It's steaming because it's so hot. It's steaming. Okay? So Luke, don't put your hand right here. Don't touch it. Put your hand on the steam. How does it feel? It's warm. Okay? Alright, that's an exothermic reaction. Okay? I'm going to bring it around. I'm going to let you feel the bottom. Okay? But listen while I explain what happened. Just touch your hand on the bottom. You'll feel it pretty hot. Okay? Alright. So the catalyst that caused the reaction actually got the oxygen to escape from the hydrogen peroxide. Okay? And as the oxygen escaped, the soap that we put in there bubbled up. Okay? That caused the foam. Now, the stronger the catalyst, okay, the higher the reaction. You could also use a different shaped flask that would cause it to kind of zoom up a little more. You're gonna feel it? Oh yeah. Pretty cool, huh? Did you feel that right? Yeah. Okay. So the stronger the catalyst, the more reaction you have, and the more foam you have. Now, if you've heard of Devil's Toothpaste, this is the elephant toothpaste. Devil's Toothpaste is the same thing, just with a stronger catalyst. So getting much more foam. I'm almost out of catalyst. It's getting hotter. Maybe, we'll see. Yes.
So yeah, like you said, the catalyst causes the oxygen to escape really fast. Normally in hydrogen peroxide, it takes a few hours for it to escape. But when you add the acetone, it makes it do it really fast. And normally it just goes. But when you add soap, it goes.
Yep. Exactly.
And also, I first learned about elephant toothpaste from Mark Roberts. He did YouTube.
Yes, I've heard someone else explain it. Okay. Yes.
So my friend said that once he tried an experiment, it wasn't very safe. So he made a big dish and he had a bottle of ice and he put a bunch of baking soda in it.
And
it foamed up really high. It got foam everywhere. It didn't exactly go like boom. It just like.
Oh boy.
It got all over the.
Speaking of boom, that's what the yeast is.
Oh yeah. Okay. You can see it kind of creating much more. It's a little warm. Okay. 2 more. All right. Here we have a highly flammable, meaning it can burn. Okay. Acetone. This is the same thing it's the same as nail polish remover. Okay. What we're gonna do, we're gonna put the foam cup into the acetone and see what happens. let me explain. Okay? Polystyrene foam is really just polystyrene. Look at it now. Okay? Polystyrene foam is really just polystyrene filled with millions of tiny little air pockets. Okay? As the polystyrene dissolves in the acetone, we release the air pockets, and what's left behind is this sticky goo. Okay? Kind of crazy, huh?
Oh my god.
Okay. Now, I can't put the air pockets back into it, so I can't get the foam back. But I am going to take it out of the acetone, and we'll put it on this paper towel and see if we can get it to dry out a little bit. And hopefully it'll make a different shape. I'll let y'all touch it when it dries a little bit. Look, can you see it? Okay. All right. Okay, so that's the melting foam. Okay, the polystyrene dissolves, and the little air pockets that are trapped in there begin to escape. It'll cause the bubbling. Okay, and all that's left behind is the little goo. Matthew, close the door, please. Okay, last one. Okay, our last one, I have some filter paper here. Okay, coffee filter paper. Okay, what we're going to prove with this one is we're going to try and deconstruct black ink. Okay, remember how we talked about black is a combination of all the different colors together? Okay, we're going to try and prove that. So, on my filter paper, okay, Sophie, I'm going to have you, Sophie, you're going to use the marker, you're going to draw a little stick man, okay, about this big, not super big, okay, but his feet need to rest on the line that I have here, okay, so it won't take super long, but what we're going to do is once Sophie draws the little guy, I'm going to fill, I'm going to fill a glass with water. Whoa. I'm going to put it in here, but I'm never going to let the ink actually touch the water. Okay? Instead, the filter paper will actually draw the water up the filter paper and cause the ink to spread out. And hopefully we'll get to see all the different colors that are actually in the ink. Yes? So bring it to me when you're done.
With the cup that how you made it dissolve,
Mm-hmm.
because that's actually what nail polish remover is made of. There's some that are pure acetone, so if your parents are having people over, don't try pouring acetone on the
Into their foam cups.
Yeah, I had to learn that.
All right, great job. You got some cool in here.
And like I'm gonna put him in the bubbly acetone.
All right, here's our little guy. Okay, I'm gonna put him in the water, but again, not gonna let the ink touch the water. Okay. A little bit of it touched. Okay, but you'll see in just a second, it starts to kind of carry the water up, and we're gonna see what kind of colors are actually in our marker. We thought the marker was black.
It's not.
Let me see if I can get them. Good.
Blue.
Maybe.
His arms are melting. His arms are melting. His
All
legs
right.
are melting.
What kind of colors do you see?
Purple and
Purple?
I see a bit of blue and some violet.
Blue and some violet.
Looks like it's light turquoise and violet. A little bit turquoise. I do mostly violet.
Mostly violet?
And blue.
Okay, so as the water is carried up the paper, it actually causes the ink to move. Okay? And as the ink begins to move, it kind of spreads out into all its different parts. collect the other classes in there. And look how it turned out. See how all the ink moved up? You can see some red, you can see some pink, there's a little blue over here. Okay? But all the ink traveled up. Okay? Here, I'll bring it up. I'll leave it until we leave. Okay? Okay. So, that's our last experiment there. But I am going to let you touch the gooey. Okay.
Oh, it's like a marshmallow that's not perfect.
No, it's not warm, but you can tell it's certainly like harder than it was before.
That feels so weird.
The juice changes color and comes back.
If you turn that, it shoots out carbon dioxide. I've never even used it again. No, you have to turn it off. Like the pink of carbon dioxide. If you did, then you can't beat.
No, I mean, like, instead of carbon dioxide, and you're
Okay. Okay, look at our guy now.
Looks like a galaxy. The yeast is overflowing even more.
Yeah, look at our yeast.
It looks like a milkshake.
Okay. So, here's what we're going to do now.